what was the key idea that allowed us to implement lock freedom. And the hint really is the one thing you should take away from this talk is that we were able to schedule fine-grained memory synchronization without locks. And then once we had this main idea, how did we then improve the scheduling mechanisms with different tactics? And finally, I will present to you like a very short case study of where I used these lock-free data structures. So let's go into the first part, which is understanding what HLS does currently. So this is a message passing example that I'm going to go through. Here we have variable X and Y. You can think of it as data, X is data and Y is a flag. And you may have one thread that sets the data and then sets a flag. So X is written to 1 and then Y is written to 1. And on the other side, you will read the flag first, which is Y, and then you will read the data X. And in this case, the assertion will be that if you see that the flag is set, then the data must be set. And you must, this assertion must hold. So what happens in HLS is that, sorry, let's adjust my screen slightly. So what happens is that HLS will, so we want to compile this program into the FPGA, and what happens is the memory locations will be directly compiled. So X and Y will be wired on chip, and each thread will then be wired to X and Y. And we will see that for the case of, for the entire talk, I will say time is going downwards. So what will happen is the HLS tool will compile the first thread and says, okay, we have a store of X and then a store of Y, and on the other side, a load of X, a load of Y, and then a load of X. And what happens here is that this program needs to obey a sequential consistency. Sorry, yep, needs to obey sequential consistency, which was defined by Leslie Lamport in 1979, I think. So what he said was, as long as the memory accesses are interleaving of each other globally, you will get correct behavior. So this is one possible behavior. And then you can see that that is another possible behavior. That's another interleaving. And then you have another possible behavior. This is the 3 different interleavings that are legal. What will happen is that in the FPGA context, you can have reordering of memory operations. And it does, so in this program, it doesn't say anything about how so the load of X or load of Y should be ordered. So we can easily end up in a situation where we can break the assertion. So what does HLS guarantee? It guarantees locks, right? So when you use a lock, let's say you use the P thread mutex, say M, and what then you have to do is you have to then inject locks and unlocks, basically. And what this will do is it will realign your memory accesses and make sure that you never hit this, you never break the assertions, and you always obey SC behavior. So based on, so let's talk about lock freedom now. So atomic operations are memory operations that are fundamental to the fundamental primitives of concurrency. Using atomics is how you build more complex data structures. Even locks can be built using atomic operations. So this understanding and supporting atomic operations is very important, but HLS hardly does it. So the question was then, what do we need to support atomics on hardware? So let's look at 2 properties that atomics requires, right? So the first property is that the atomic access must be indivisible. That means no other operation can come in between this operation, and all threads should see the updates at the same time. And this is basically guaranteed now, given the current HLS compilation that is compiling, say, X and Y just now as a directly mapped, memory, and it is all on chip. And so this was the first assumption that we made, right? And this, so if this holds, then the second property that you need to obey is particular ordering constraints. So in the C memory model, it will say, okay, atomic operation has to happen in this order, and it cannot be reordered with any other operations in its thread. And that is kind of a typical scheduling problem in HLS. So that's the key idea here. We noticed that as long as the memory operations are indivisible, then you can get away with just scheduling constraints to strengthen the memory model. And using this understanding, we can also support weak atomics. Now, weak atomics are basically atomics that do not need to obey SC behavior, which means you can reorder them more freely, but they still have to order certain ordering constraints. And I'll come back to that later. And so this is the key idea that we had, the base of our work, right? So we have this program again, and now we want to use atomic operations instead. So we get rid of the mutexes and all the locks and unlocks, and we say, okay, I want to make Y atomic, right? In this case, what we need to guarantee then is you need to make sure, but what legup will do is that once it sees this atomic keyword, it will then inject its own mutex and try to order all the memory operations. So this is what legup does when it supports OpenMP atomics. So it will re-inject these locks and unlocks. So this is kind of counterintuitive because the software world thinks that you use atomics to build locks, but in HLS, we are using locks to build atomics, which is counterintuitive. So that was an interesting observation. And so what essentially we did was we looked into how we can schedule atomic operations, right? So we just needed to strengthen the memory model by looking at the program and saying, okay, Y is atomic, so it can't be reordered with X anywhere. And so we get rid of the locks that legup injects, and then we simply add scheduling edges. And by ensuring that these intra-thread operations are ordered, we are able to ensure global synchronization correctly. And so this was the first piece of work that I did. And I implemented this strengthening of the memory model in legup 5.1 using LLVM, where, as I said, we looked at each thread and we looked at the atomic accesses and we injected extra scheduling constraints to restrict the ordering behavior. And I evaluated it on 3 different state-of-the-art data structures: the Trabia stack, the single producer consumer circular buffer, and the Michael Scott queue, which in terms of complexity, it goes down that way, right? The stack is the simplest program with the fewest accesses, and the Michael Scott queue is really complex and does multiple producer, multiple consumer behavior. And so I also arranged these data structures into different patterns for experimentation. So I had 3 different patterns which I called chaining distribution and reduction in my papers, but it's actually one-to-one, many-to-one, and one-to-many behaviors that we test. And I scaled the number of threads basically up to 10. And you can see in my papers the full results, but what I want to show here is a distribution of my results. So on the left, I have the run times of, and the y-axis is the runtime of scheduling atomics using my approach, and 2 different legends are basically legup's approach of doing just locks and implementing atomics using locks. And so we see that scheduling atomics basically deserializes memory synchronization. So most of these benchmarks, what happens is legup injects 1 lock and ensures that all the memory accesses obtain that lock, and that kind of serializes all the accesses. And the moment we use scheduling, basically we break this serialization and make it runs much faster. And also on the right, you see the LUT count. You see that the scheduling approach is using either the equal number of LUTs or lesser. So, and these speedups vary by the type of data structure, the pattern that I was talking about, and the number of threads. So that is very detailed and is in my papers. I can point you to that if you want to look at it later. So that was the first part, right? We were able to show that simply by removing the locks and just injecting scheduling constraints, ensure that we can run much faster and you require less resources. And this was a really simple observation that gave us a good starting point. And so the next question is, how do I improve on this, right? And so I will present three different tactics. So the first one is global analysis. The second one is implementing weak atomics. And the third one is looking into pipelining and how we can achieve scalable analysis. So let's look at the first one, which is global analysis, right? So what I mean by standard local analysis here is that this is what a leg up compiler will do, right? It has three threads. You first look at the first thread, do some alias analysis, and then figure out that, okay, whether it has any aliasing constraints. And then it will inject the thread, the memory operations to the scheduler, and that will result in a schedule on one particular compute model unit, and then it's then wired to shared memory if required, right? And so what happens then is it will look at each of these threads one by one and do the same operation. So let's say we have this program, right, where I have X and Y are both atomic, and the standard local analysis will say, okay, I look at the first thread and I have store to X and store to Y on the first thread, and then I have a load of X in thread 1 and a load of Y in thread 2. And basically what our local analysis will do is say, okay, I need to guarantee this behavior in case we have message passing in other threads, but that's not the case. So what we did was we implemented global analysis, right? We looked at the entire program to generate scheduling constraints for each thread. And in this example, what we will be able to notice is that actually we don't need that edge and we can actually run in parallel. So this was an important observation. And the way we handled this was to look into the C memory model definition, right? So we have the same message passing program, and the C memory model basically says that there are inter-thread synchronization opportunities across atomic operations to the same location, which are in different threads. So this is the definition that we use. So we say these two operations can synchronize at runtime. So here in this program, Y can synchronize at runtime directly. And as a consequence, when we do analysis, because the y-axis can synchronize, that means that the x-axis can indirectly also synchronize via a path of execution. And so we need to ensure, so we need to ensure that these orderings are preserved, right? And we also can redefine CanSync to support weak atomics, which I'll come to it slightly later. And it's not enough to just consider pairs of synchronization paths, right? For example, here we have a message passing example, but it's going through three threads. So if we just focus on the first synchronization, you'll say that, okay, the x-axis, the store of X can't synchronize with the load of X. But then if you continue down that path, and Z is an atomic operation that synchronizes with the third thread, then you need to guarantee that the two store accesses to X have to be in order, have to synchronize, and therefore you need to ensure ordering. And so basically, in general, what we are looking at is a path enumeration problem, right? So, and we have a set of constraints for our path enumeration. So the first constraint is that paths must be alternating between program order edges and CanSync edges, right? And the start and end of this path enumeration must be to the same location. Also, if the start and end are loads, they must be atomic loads. If not, it's not possible for them to be visible. So this is like a C memory model quirk. And finally, the parts must never return to the same thread. And using this path properties, we can see that and then what you do is you just extract the PO edges, which are the program order edges, and give this to the scheduler of each thread, which will then be able to schedule these operations in order. And what happens is, if you have a different um, operations in your thread, for example, here I've just randomly inserted other operations which are not connected by any program order edges that we need to preserve, they can actually then run in parallel. So we basically have 5 properties for path enumeration, and we go through the entire program, and then we feed it to our global, into our local schedulers. So we have a global analysis that looks into the entire program but generates intra-thread constraints. And the second part that I wanted to discuss was weak atomic. So the C memory model describes several weak atomics that do not need to obey SC behavior, which means they can be reordered more freely. So we support 4 different atomics, which is SC, acquire, release, and relax. And basically how the C memory model allows you to define these things is you have to add it as an extra parameter, as you can see in this example. So acquires only work for loads, stores, releases only work for stores, and relax works for both loads and stores. And so based on the C memory model, we can define, so if you were not to consider the weakness of the atomic operations and this current CanSync definition that you have on the slide now, then you will have bidirectional synchronization opportunities. And what happens is you will have this behavior, and where you can have this path enumeration where you need to preserve all the memory order edges. But if you consider the weakness of the operations, then you can see that actually the release and acquire definitions say that you only need to go in one direction. So in that case, you won't have this synchronization opportunity, and therefore you won't need to then inject any path and any program order edges, and you can run them freely. So it is always been the case that weak atomics is slightly notorious, and it's very subtle, and it can be buggy if you don't implement it correctly. And so what we did was we took our path properties and we took our CanSync definition and we checked it against the C memory model, which is the ground truth. And we gave it to a bounded model checker called Alloy, where you can define the properties and the number of events. And Alloy basically will give us counter examples for where our path properties were too weak. And we were able to generate up to 7 or 8 events. So the bound was 7 or 8 events, which is quite a big number of events for verifying memory models if you look into the literature. And the third tactic was basically loop pipelining. So in this case, we have, here we have an example again of a program which, in this case, X is atomic, and we have a for loop that's basically writing the index of the for loop into both locations. And what we had to do is we had to consider not only one iteration, but also the next iteration. And even LegUp does this. And so the standard approach would be then to inject locks around the atomics, right? You have to add back, you have to basically ensure that all the operations run in sequence and even across iterations. And basically it will prohibit any overlapping between iterations so what will happen is your latency and your II will be the same, your initiation interval. And so what we did with the first piece of work was that we looked at this and said, okay, can I also do loop pipelining just by using scheduling constraints, right? And so that's what we could do. So we basically injected uh, intra-iteration constraints into the leg up scheduler, which allowed us to remove the locks and ensure that we can run faster. But in this particular case, local analysis didn't allow us to reorder operations. But we will see that if you go further and do global analysis on this program, and if this is the only thread in the program, then basically what you need to ensure is only aliasing edges are ensured across iterations. So you can remove a lot of those edges and they can basically run much faster. And the whole idea is that using locks, you were never able to overlap iterations, but using atomics with scheduling constraints, you can actually overlap iterations. And the main issue that we stumbled into beginning of our work was that our path enumeration can scale exponentially, and the base is basically the number of edges that go across threads, right? So the possible synchronization opportunities. And we saw a lot of cases where the programs looked like this, where you had overlapping can sync edges, right? So a lot of it is got to do where you read a certain value from a location, you do some processing and you want to update it, and another thread looks at the same location and wants to, you know, update it as well. So this happens with compare swap a lot. And what we had to do is we realized that this is overlapping and we need to do something and try to reduce the exponent base. And we basically looked into considering removing these overlapping edges, and during our path enumeration, we only consider the primary edges, which do not overlap. And using this initial result, we can then post-process and reconstruct the edges that we require using visiting the overlapping edges and also visiting the aliasing edges. And we were able to obtain the same results as the naive implementation. And I will show you some timing results in a short while. And so this is a graph showing the tactics, the three tactics that I was talking about. So on the left again is runtime, and on the right is LUT count. And we see that each tactic individually improves memory scheduling. So the biggest gain, I would say, is probably from implementing weak atomics. And then you get gradual gains, then implementing global analysis. And then finally, when you do pipelining, it gets even faster, right? It's quite consistent if you look at this plot. And the resource utilization really varies between the latency of your thread and also the II. So I noticed that in leg up, if you increase the latency, you get for the same number of operations, your area increases. But and also when you decrease the II, you have the same behavior where you have to pack more things, but you need more circuitry. So that also increases area. And so this is the results that I have explored in terms of, you know, the benchmarks and the data structures that I was experimenting on, and also the patterns and the number of threads. And this is the analysis time. So on the left, we see the x-axis is basically our optimized analysis. On the y-axis is our optimized analysis. The left x-axis is basically thread local analysis, and the right was the naive global analysis. And we see that thread local analysis is way faster because it doesn't need to do any complicated thing. It just has to do one probably O n pass, and that's it. You already know what the schedule constraints are. But with naive analysis, you see that sometimes most of the time it's slower than the optimized version. Sometimes the optimization is actually making the analysis time slower. And this is mostly when it's the case for weak atomics. So weak atomics and our optimization basically has the same kind of effect where it removes synchronization opportunities. And so if you already use weak atomics, doing the optimization can be redundant, but you can treat it as like a safeguard to ensure that you never not obtain a result for a large number of programs. And so now I just go into the last part where we saw a lot of like the works and the tactics and everything. And the question is now, where is this really useful, right? So what I did was I implemented a case study in my last chapter of my PhD, which basically looks at PageRank. And PageRank basically, in a nutshell, ranks web pages using the graph of web pages. And the baseline implementation that I took from Panosha basically has two for loops, which first visits all the nodes, and then the inner loop visits all the edges which point to its neighbors. And the ranks are weighted and the updates are actually atomic. So it has a compare and swap in the base implementation. And the Panosha benchmark suite has PageRank, and I took it out of the box and I implemented it in LegUp. And basically you see sort of the hardware architecture looks like this diagram where you have the circles are the memory the RAMs. Basically you have the rows and columns of the sparse matrix, and then on the right you have the input ranks and the output ranks. And basically you have two squares or two compute units that are doing these two for loops and the weighted updates basically in sequence. And I noticed that there are basically 4 stages that I can partition PageRank to and implement streaming. But what I wanted to do is I wanted to use lock-free streaming. So basically I manually partitioned PageRank into 4 stages, and I injected lock-free buffers between all these stages. And I was able to achieve an II of 2 using all the tactics that I had. And I also implemented lock-free DQs, which then was able to share the graph load. So in PageRank, even if you partition the nodes statically equally across the different compute units, you visit a different number of neighbors. So that generates a different workload for each compute unit. And basically you may end up in a case where one compute unit is sitting idle while another one is doing work, right? So what I did was I used the lock-free data structure to share the workload. And this is all manual software transformations. I did not touch anything in the RTL. And now what I did was I gave these transform programs to all the analysis that I built, the arsenal of analysis that I built, right? And so this is a graph showing basically I had the blue lines are the local, the baseline I took from Panosha. The red lines are the streaming implementation using the lock-free buffers, and the green line, sorry, are the load balance streaming implementations, which use both the buffers and the DQs. And the lighter lines are basically local analysis, and the darker lines are global analysis. And so you see immediately using lock-free streaming gives us a boost of almost 3x. And my II is 2. So it's really good. And you would not be able to do this with a lock design because you will not be able to pipeline the streams unless you use some specific channels. I think LegUp has a specific implementation of channels at the moment, which I did not explore at the time, but the difference is that there you need to rewrite your program to use a specific library, and this is more generic. It's all just C++ code, but it uses atomics. And also what you can see is that when we do load balancing, which is also lock-free, you can improve the compute, the throughput even more, right? So it was almost 1.5x. And global analysis everywhere, when you turn on global analysis, you improve the throughput dramatically. And overall, it's about 30% faster, but you have a lot of cases where that's much bigger. And so also when I use global analysis, I needed to make sure that I was able to synthesize such large programs, right? So I was able to go like up to 5 or 6 compute units, which is about 30 threads. And I needed to be able to handle this load. And using my optimization that I discussed, I was able to handle quite a large number of programs. So at a maximum of 30 threads, which was about 1,500 instructions in the program, I had almost 10,000 program order edges that I needed to consider, and hundreds of synchronization opportunities that are going across threads. And I needed to be, and our optimization basically was able to make sure that I don't get exponential growth in my scalability results. And so to conclude, basically, we first saw that there's a unique opportunity to do HLS, uh, to do lock-free synchronization in HLS just using scheduling, right? So I was able to synchronize fine-grained concurrency with weak atomics that shared across multiple threads in on-chip. And I was also able to do loop pipelining. So the first jump from just removing the locks to adding constraints gave me about a 6 times speed up on my experiments, and then applying the various weak atomics, loop pipelining, global analysis gave me considerably improved my speed ups. And finally, I also implemented a lot of lock-free data structures in quite a well-known application like PageRank, and showed that you can benefit from there as well. And my focus was in my PhD was that the memory elements are directly mapped, and they're on chip, and you can access them with low latency, right? But this is the base assumption that I made, and it will be interesting to see what open works that can be done when these assumptions are not true. And finally, I hope that, you know, from this work, there can be a lot of lessons learned for other people who are also looking into HLS, improving HLS compilation. With that, I end my talk.
All right. Thank you, Nadesh. It was extensive. So hopefully there are questions from the audience. Okay, so while we wait, maybe I had a quick sort of warm-up question. So did you notice any differences in enforcing these kinds of constraints when dealing with on-chip versus off-chip memory operations?
I did not venture into the off-chip space because there was going to be a lot of engineering work required. So halfway through the PhD, I thought I could hook up the LEAP memory system into LegUp, but that was going to take time. So the difference is, what happens is when you have off-chip memory, you also have to inject fences.
Right.
So that would be the key difference. So you'd have to enforce ordering edges, but you won't be able, or you will have to introduce fences. You won't be able to remove certain fences, or you will have to introduce certain fences at different places.
That makes sense. So yeah, I think I was a little confused about how the scheduling would work in presence of this sort of data dependent latencies for certain operations, right? When you have like hundreds of threads, for example, how would you coordinate the scheduler, right? If different threads are making off-chip operations, each of which could take a varying amount of latency.
Right.
So you didn't consider that right now.
I did not consider that, yeah, in this PhD, but I am looking into it at the moment. And so, but the point was I could show something that works on chip, and it works really well, right? So you have very localized synchronization that is cheap, and you can express it in a lock-free way.
Right. Yeah.
And so the moment you go off chip, that's also another big topic. I think what we will have to separate those two things, and so have some sort of other threads that are dealing with off-chip accesses, which can then stream data into this part, right? So this is the more on-chip version, and then the off-chip version needs more thought into the whole
Right.
process.
Right. Yeah, OpenCL certainly has fences and barriers across a work group and across sort of the complete set of threads, and that could be tricky to implement at high frequency, right? That you have to coordinate across all these threads, and then your scheduler has to, the offline scheduler now needs to be aware that some things might be happening at runtime.
Yep, and also OpenCL, I think when I did some exploration, they have a load stock queue which also serializes operations. So that's another thing that we need to look into.
All right. Any other questions from the audience? Okay, if not, then thank you, Nadesh, for this extensive, wonderful talk.
Nice.
Sorry. I was going to say, next week we have a talk by Cerebras, possibly the last talk in the series. If there are other volunteers who queue up, maybe we'll extend the seminar series into October, but barring that, yeah, next week will be the last presentation for now. All right. I'll upload the recording shortly later today and upload a link to the Slack channel.
Sure. Thanks for inviting me. Hopefully I can get some questions offline or
Sure.
See if anyone's interested in any specific parts. I can also point them to stuff.
Sure. Thanks a lot.
Thank you.